Hello everyone, welcome back to Calc 3, and today we're going to start section 14.6, tangent planes and differentials. Now we already saw the definition of a tangent plane for a level surface in the last lesson, so let's review that briefly. So we have a level surface, a function of three variables equal to a constant. Then if we want to find the equation for a tangent plane at a fixed point, x naught, y naught, z naught, we calculate the gradient at that fixed point. That gives us the components of the normal vector, because the gradient is the normal vector for the tangent plane. And then the equation of the tangent plane is given by this expression here, this equation. Right? So it's the partial derivative with respect to x at the given point times x minus x naught, plus the partial derivative with respect to y at the fixed point times y minus y naught, plus the partial derivative with respect to z at the fixed point times z minus z naught. So that we saw in the last lesson. Now, what happens if instead of a level surface, we think of a function of two variables, right? So now I'm just changing the context. We say that z is equal to some function of two variables, f of x, y. This also gives us a surface, right? For every x, y in the plane, we get a z value that gives us the coordinates of a point in space. And as we go through the plane, that maps out a surface. If we assume this is a differentiable function of two variables, meaning that the partial derivatives exist and are continuous on the domain, then we can define the tangent plane to this surface, f of x, y, or this function z, at a fixed point, x naught, y naught, z naught, where here z naught can also be represented by the function value, f of x naught, y naught. And this is the expression for the tangent plane. Z equals z naught plus the partial derivative of f with respect to x. Now this is a function of two variables, evaluated at x naught, y naught times x minus x naught, plus the partial derivative of f with respect to y at the point x naught, y naught times y minus y naught. And here we can replace this z naught with f of x naught, y naught. So everything is in terms of x naught and y naught. X and y are variables. X naught and y naught are our fixed points. Here we have two partial derivatives, and our function value for the tangent plane is given as this z. So we plug in an x, we plug in a y, it gives us a z. Those three numbers together give us a point on the tangent plane. Now, a natural question would be, are these definitions compatible? Have I just defined something new, or is this exactly the same thing, just with a different context? And they're the same. So to get an idea of this, let's take a look at something. If I were to take this function, z equals f of x, y, and I were to rewrite it, just subtract f of x, y from both sides, I get z minus f of x, y equals 0. Now I can define z minus f of x, y as a function of three variables. Let's call that capital F of x, y, z. And if I set capital F of x, y, z equal to 0, then I'm going to have a level surface. And I can take the partial derivatives of that capital F function. And if I take the partial derivatives, well, there's no x's or y's involved here. So if I take an x partial and a y partial, it's just going to be minus the x partial and y partial of this lowercase f function. So the gradient of capital F is negative f of x, negative f of y, and 1. There are no z's involved here, and the partial derivative of z with respect to z is 1. So now if I take this gradient of this capital F function and I plug it in, excuse me for a second, let me bring this back down. If I plug this into the formula we already had of my level surface, I get this expression. Negative partial derivative of lowercase f with respect to x at x naught, y naught times x minus x naught minus the partial derivative of lowercase f with respect to y at x naught, y naught times y minus y naught plus z minus z naught, because remember the partial derivative with respect to z was 1, equals 0. And this is exactly the same thing that we got up here. We just solved this equation for z. So these are compatible definitions. They're the same thing, it's just now we're given a different context. Is this a function of two variables, where the function value gives us a z-coordinate, or are we talking about a level surface that's a function of 3 variables and we say it equal to a constant? Either way, we can define the tangent plane exactly the same. We can even think of this from another perspective, right? We didn't go over this in detail, but I did mention it in lecture one day, that if we're taking partial derivatives and I want to think of a line going in the x or y direction, then the direction vector for those lines can be given in this form. So I have a function of 2 variables. I want to think of a tangent line strictly in the x direction. So I'm going in the x direction. I'm not going in the y direction at all. Then the z component of this direction vector is given by the partial derivative with respect to x. And now if I do the same thing in the y direction, I'm not going in the x direction at all. I'm going in the y direction, and then the z component of that direction vector is given by the partial derivative with respect to y. Right? This tells you, if you remember these partial derivatives, this tells me how the function is changing, the function values, the z values, are changing in the x direction. This tells me how the function values, the z values, are changing in the y direction. So these are 2 direction vectors for 2 different tangent lines. They both lie in the tangent plane. So if I wanted to find the normal vector for the tangent plane, I have 2 vectors in the plane. If I cross them, I get the normal vector. And so if I cross these 2 vectors, 1, 0 partial derivative of f with respect to x crossed with 0, 1 partial derivative with respect to y, I set up my determinant, I take a cross product, I get this negative partial derivative with respect to x, negative partial derivative with respect to y, and 1. And these are exactly the components of the normal vector I got here. So everything kind of comes together, and everything is compatible and makes sense. So that's how we find the tangent plane for a function of 2 variables. Same idea as before, just now a slightly different context. And I want to give a different context to these tangent planes. And to do that, actually let's just go ahead and do this. To do that, let's go back to Calc 1 for a second. So in Calc 1, we know we have a function of 1 variable. We graph it, it gives us some curve in the xy plane. And if it's differentiable, we can find the tangent line, right, where the derivative gives us the slope of this tangent line. And in Calc 1, what we did was we'd pick a point, find the equation of this tangent line, and we'd say, okay, close to that point we picked, the tangent line is a good approximation for this function. Right? And so this tangent line was usually a simpler equation. So instead of having to plug numbers into a complicated equation to find function values close to this point, we can use this simple line to find function approximations of function values close to this point. So if I stay in this area, it's a pretty good approximation. If I go too far out along this line, right, that's a bad approximation. This is a bad approximation. But close to the point where they're tangent, that's a good approximation. We're going to do the same thing with surfaces. For surfaces, though, we're not going to use a tangent line. We're going to use a tangent plane. So let's define this linearization. So let's say we have a function of 2 variables. We call this function L of xy, which is equal to f at some point x0, y0, plus the partial derivative of f with respect to x at some point x0, y0, times x minus x0, plus the partial derivative of f with respect to y at some point x0, y0, times y minus y0. This is called the linearization of f at the point x0, y0. Okay, so all we're doing here is say we have some surface. This surface can be described by a differentiable function of 2 variables. And we want to find a linear approximation for this function, a linear approximation for this surface. And we just use the tangent plane, right? This f of x0, y0 can be thought of as a z0 variable. And this is exactly the equation for the tangent plane. It's just the context is different. In the previous context, we were thinking of the tangent plane as some geometric surface. Here we're thinking of this as a function of 2 variables. that we can use to approximate this function f, right? So the value of this function L, they're called linear approximations or tangent approximations of f. And so I've already said this is L of xy is a function of two variables. So we plug in an x, we plug in a y, we get some third value. And this third value is going to be very close to f of xy for points close to x naught, y naught. If we're close to x naught, y naught, we get something close to f of xy. If we go too far out, just like the example from Calc 1, if we go too far out, it's a bad approximation. And I have a crude drawing here, but the idea might be better than my drawing. So here I have some surface. This actually wouldn't be a function of two variables the way I've drawn it because it doesn't pass a vertical line test, but we can use our imaginations, right? Say maybe I've just tilted things a little bit. So I pick a point, I draw a tangent plane at that point, and you can see that in this region, this might be a decent approximation. This tangent plane might be a decent approximation for this blue surface. If I go too far out, though, this tangent plane is pretty far from this surface. So it's a similar idea, just using geometric objects of larger dimension. Right? In order for this linearization here, this function of two variables that can approximate our function f, in order for this to make sense, f has to have continuous partial derivatives, has to be differentiable at the point x naught, y naught. Otherwise, it doesn't make sense to talk about these things. And what else? Notice that if we take the point x naught, y naught, and we plug it back into this approximation, this linearization, then we plug x naught in here, this whole term is going to disappear. I plug y naught in here, this whole term is going to disappear, and I'm just left with f of x naught, y naught. So at the point x naught, y naught, this is the tangent point, L and F agree, they're exactly the same. And that makes sense because that's the point where we're finding the tangent plane. That's the point where we're starting our linearization. So they agree at one single point, at least one, most likely only one, unless this surface is also a plane. And in a small region around x naught, y naught, it's a good approximation. So let's do an example. Why would we even want to consider doing something like this? So let's find a linearization for this function z equals the square root of 6 minus x squared y squared at the point 1, 1, and then use that linearization to approximate the function at 1.01, 0.97. So first, here's the equation for the linearization. We know that we want to find the linearization at the point 1, 1, so I've plugged in 1, 1 for all the x naughts and y naughts, and now I just need to find these partial derivatives and this function value. So first, the function value, all I have to do is plug 1, 1 into this function. So it's the square root of 6 minus 1 squared minus 1 squared, which is 2. For the partial derivatives, I actually have to take these partial derivatives. So I can think of this function as 6 minus x squared minus y squared, the whole thing to the power 1/2. So if I take a derivative with respect to x, I get 1/2 6 minus x squared minus y squared to the negative 1/2 times the x partial derivative of the inner function, which is negative 2x, which simplifies to negative x over the square root of 6 minus x squared minus y squared. If I plug in 1 for x and y, I already saw that this denominator becomes 2 because it's the same as the function value. So this is negative 1/2. When I take a partial derivative with respect to y, things turn out similarly, right? I get this first part is exactly the same, and all it changes is this last part of the derivative. And so this partial derivative with respect to y is negative y over the square root of 6 minus x squared minus y squared. I plug in 1 for x and y. I also get negative 1/2. So now this gives me my linearization. Our first answer, 2 minus 1/2 x minus 1 minus 1/2 times y minus 1. This is the linearization about the point 1, 1. Now, you might want to distribute these things and simplify things, but in our case, we're not going to, because we're actually going to plug in the point that we want to approximate from here, and leaving it like this is going to be useful. So I want to find an approximation for the function value at 1.01 and 0.97. This point is pretty close to 1, 1. I can use this linearization. So if I plug in 1.01 for x, 0.97 for y, now these subtractions are pretty easy. 1.01 minus 1 gives me 0.01. 0.97 minus 1 gives me negative 0.03. The only difficult part here is I have to multiply these by a half, but I'm sure you can do that. Just divide each of these terms by 2. I get 2 minus 5 thousandths plus 15 thousandths. So this really is 2 plus 100th, which is 2.01. And that's my answer. That's the approximate function value at 1.01, 0.97. So why is this useful? This is useful because if I wanted to do the function value by hand, right, f of 1.01, 0.97, I'd have 6 minus 1.01 squared minus 0.97 squared, take the square root of that whole thing. Now these squares you could do by hand. It'd be a little annoying, but you could do it. The subtraction might be a little annoying, but you could do it. But the square root, you're going to have some ugly decimal. You're going to have to take the square root of that. What's that going to be? I don't know. It turns out to be approximately 2.0097265, and it keeps on going forever, which is approximately 2.01. So for a lot less work, we get an approximately good answer. Okay, this video is running a little long, but let's just quickly go through one more thing. We can also do this for functions of 3 variables, right? We just lose the geometry of a plane, and we'd have to talk about hyperplanes, which we're not going to talk about. So for a differentiable function of 3 variables, we can define the linearization at a point x naught, y naught, z naught, and now we have a fourth coordinate, f of x naught, y naught, z naught. And we define the linearization as a function of 3 variables, and it's the same definition. We have the function value plus a partial derivative with respect to x evaluated at the same point times x minus x naught plus a partial derivative with respect to y at the point times y minus y naught. And now we add a fourth term, the partial derivative with respect to z evaluated at the point times z minus z naught. And now you can abstract this definition, make it for as many variables as you want. Let's say I had a function of 10 variables. You could define the linearization about a function of 10 variables at a point. It's just going to be the function value plus each partial derivative times the variable minus that point. And so if we had a function of 10 variables, the linearization would contain 11 terms. The function value and then one term that's a product of each partial derivative times that variable minus the coordinate of the point. Okay, let's stop there for now. In the next video, we'll continue 14.6, and we'll talk about some more useful approximations and other ways to use tangent planes and similar ideas.